Hello, everyone, and welcome back to our µTAS 2021 YouTube Live series. Today, we'll be featuring to be presented at µTAS research teasers from around the world, starting now with Europe and Africa. I'm excited to introduce our first guest, Professor Basabe from the Microfluidics Cluster of the University of Basque Country in Spain. Take it away.
Hello there. Thank you, Ryan. Hello, everyone. So it's my pleasure today to introduce the work that we usually submit to µTAS and also to tell you a little bit more of what we are aiming to submit this year. This is all to encourage you to attend µTAS, which, as you know, is the leading conference for microsystems for chemical and cellular monitoring. My name, as Ryan said, is Lourdes, and I am the director of the Microfluidics Cluster in the University of the Basque Country. Let me show you some work that we submitted recently to µTAS during the last couple of years, where we developed microfluidic devices for self-powered microfluidic devices. The aim was to develop some type of universal architecture that could be useful for many different applications. This consists of modular micropumps made of polymers that can be assembled to polymeric microfluidics cartridges. Recently, we showed that we can even fabricate these micropumps by 3D printing, making it more affordable and suitable for many different types of labs. In the videos, you can see some fluidic operations that you could perform with this type of micropumps. This work that was previously submitted to µTAS is now published. It was recently published in Industrial Engineering Chemical Research and Sensors and Actuators. Another work that we submitted last year to µTAS when the event was online actually was the manipulation of water droplets using magnetic forces. For that, we described a tunable super paramagnetic ring for droplet manipulation, which is formed by the interaction of ferrofluids with water droplets when the ferrofluid is under a magnetic field. As you can see in the pictures, when the ferrofluid is under a magnetic field, it forms instabilities, and when these instabilities are formed and it gets in contact with a droplet of water, the droplet gets stabilized by the ring. The ring becomes now also a magnetic instability, and it keeps all the different droplets stable. As you can see in the videos, we can even, using this approach, we can achieve hanging drops that can be manipulated, translocated, and moved by magnetic forces. In this video, in the bottom, you can see also the translocation in a normal surface. As you can see, the assembly between these two liquids, the ferrofluid and the droplets, becomes like a cupcake, and the droplets the water droplet is now optically addressable because the ring is only confined at the bottom of the drop and is covered by a very thin layer of oil. The ferrofluid is oil-based, and that thin layer of oil can be removed if needed. This could also be useful for mixing of droplets. What you saw there are two droplets together. They are separated by the ferrofluid, but when the magnetic field is removed, the ferrofluid collapses and the two droplets can mix, as you can see here now. Okay, so we can mix the droplets. So let me tell you, this was something we submitted to µTAS last year. The work was finished during this year and it's now accepted for publication in Advanced Functional Materials. Instead, this year for the µTAS 2021, we will submit several works. Within the microfluidic cluster at the University of the Basque Country, we try to work with smart materials, different type of microfluidic platforms like paper and plastics, magnetically actuating materials, and also devices for cellular studies. So you see here 4 tentative titles for the work we will submit. As you can see, some devices for colorimetric determination of nitrates, magnetically actuated debubbler for microfluidics, optical micro device for monitoring cell adhesion, and other alternate bit biosensors for the determination of lactates. So as you can see, we try to combine smart materials with microfluidic platforms for different applications. But we are very, very excited about a work that we want to present also, which is multifactorial microenvironments control and cellular monitoring platform. We believe that with this type of platforms, we can control different factors of the microenvironment, and we at the same time, we can monitor different aspects of the cells, and we believe this could be very useful for cellular monitoring and cellular studies. So this year, like every year, I will encourage all the people in my group to attend the µTAS. We usually are present as much as we can, even if it is in person or it's online. And I encourage you all to attend, since this is the conference for the microsystems and for chemistry and life science. So please submit your abstract. Thank you.
Great. Thank you so much for sharing all of that. And congrats on the Advanced Functional Materials publication. That's awesome. All right, so thank you so much again. Next, I would like to introduce Professor Descroix from the Institut Curie in France. If we want to switch for the sharing of the screens.
Yeah, sorry. How do I do that?
Oh, you're good. You're good, Stephanie. You can just, looks great.
That's great. You see my screen? Okay.
Yes.
So I'm Stéphanie, and I'm very pleased to be with you today, because I must say that I really like the µTAS conferences. I think I'm quite old now. I have attended a lot of them, but each time I'm still surprised, and I always have a lot of fun and a lot of very interesting science. So I'm coming from Paris, but today it's not exactly the weather that you can see with the Eiffel Tower, unfortunately. But I'm sure that when we will be in Palm Springs, we will have a very sunny weather. So as Lourdes, I will show you some of the work that we develop in the team and that we have presented at µTAS. In my team, we have 2 types of activity. One is related to organ on a chip. And for years, we have been working on the development of new models. And this one is one of them, where we work on the intestine. And as you can see on this images and movies, you can see the 3D structure that we have been able to obtain, starting from collagen structure and using mouse intestinal organoids. But the aim of this work was mainly not only to reproduce the epithelium, but also to work on the reproduction of the stromal compartment. And I won't go into details, but I would like just to show you a very beautiful picture to tell you that our aim and our really challenge in this work was to be able to show that you need both types of cells in this 3D structure in order to replicate on chip the proper segregation and differentiation that exists in vivo in the intestine. And the other type of activity that we have in my team is that we like to play also with microfluidics for bioanalysis. And in particular, we like to play with droplet, as you can see on this movie. And I think that we have the same types of games with Lourdes, because we like also to play a lot with magnetic particles and droplets. And we have been working on this aspect for a while, but more recently, we try to move and to change our scale in order to move to single cell approaches. And for that, we have presented, I think it was last year by Simon, this work where we were able to work with droplets in the picoliter range and to extract from these very tiny droplets some magnetic particles in order to perform some single cell analysis. So this is what has been already presented, and for most of this part, it has already been published. But this year, we also aim to show you some new works that we have been working hardly for the last months. And one of them is the work of one of my PhD students, Man, who is working on the development of a muscle on a chip, but not only a muscle, we try also to get this muscle that could be innervated and also vascularized. And we spend some time to answer the question that I put here, is how are we able to get this type of muscle with the beautiful striation and the multinucleated cells? Because at the beginning, when we started the experiment, basically we just get this monolayer of muscle cells, and you can imagine that it does not look like in vivo situation. And we spend some time to show how the geometrical cues will be really important to reproduce a muscle that will get the proper organization in terms of fiber. So this is one of the answers that we will try to discuss. This is one of the projects we will try to discuss with you in the next µTAS, if it's accepted, of course. And another one is still related to these magnetic particles. And recently we have been working on one of the important biomarker for cancer that people call the Hermes, like the Greek the Greek Hermes, that will give a lot of information about cancer. So here we are working on exosome extraction and purification. And for that, we have been developing already a few years ago this system that you can see on this movie, where you have magnetic particles that are subjected both to a drag force in this direction and a magnetic force in the other direction, so that you can keep them as a quite dense pack bed of particles in order to perform extraction. And recently we have shown that we were able to use this system to perform the extraction of this vesicle, but not only, we have been able to use this to extract different subpopulations by coupling different of this fluidized bed in order to extract different subpopulations with different protein surface expression in order to get more information about this exosome, especially in the field of cancer. So this is part of the job of the work that we will present you during next µTAS. And then one of the reasons, honestly, I would like to go to µTAS is really to be able to leave my home at some point. I must say I won't leave my parents, but I will leave my kids and my husband. But this is for a very good reason, because I will be able to meet my friends, because I must say that now I think that I have a lot of friends at µTAS, and it's always a pleasure for this human reason, and this is a really important one. But not only, as I said at the beginning, I'm always surprised and I feel really rich when I come back from µTAS, rich of many ideas and discussion. And I don't know, for the one who have never attended, you should realize that when you are in front of your poster, I think this is really the place where you have a so huge number of interesting discussion, interaction, and feedbacks on your work that it's really really important, I think, in the career of young people also to experience this type of situation. And regarding also the scientific aspect, I must say that as a scientist, I'm really convinced that what we develop in the field of organ on chip could be really important, but not only for the question of drugs, killing, and so on that we always mention, but I think also for all the basic research, both in biology and biophysics. And I must say that I'm quite excited by some of the plenary speakers that have been invited also to the next µTAS. So I hope I will see all of you at µTAS, hopefully directly in Palm Springs. And I say see you soon. And now I stop sharing my screen.
Thank you. That was great. Yeah, so obviously organ on chip is a big thrust for the microfluidics community at µTAS, and so I'm excited to see a lot of that coming up at µTAS 2021. And so last but not least, we have Professor Abdelgawad from American University of Sharjah and Asut University in Egypt.
Well, good morning, Ryan, and thanks for having me. I'm excited to be talking about the project we presented before at µTAS and the extension that we hope to present again in µTAS. And the title of the project is Mechanical Properties of Endometrial Cells as a Biomarker for Endometriosis. I'll just give one slide as a background about endometriosis in general. So it is presence. It's a medical disorder characterized by presence of endometrial cells outside the uterus. It causes chronic pelvic pain, infertility, and increased risk of ovarian cancer. It affects about 5 to 10% of women in their reproductive age, and which is about 170 million women worldwide. The gold standard for diagnosis of endometriosis, unfortunately, is laparoscopic surgery, which is expensive and physicians are reluctant to use surgery just for diagnosis. So a suspected patient can wait up to 8 years before she's definitely diagnosed with endometriosis. So we thought of, can we use microfluidics and its capabilities to come up with an unconventional biomarker for endometriosis or not? And what we thought of is mechanical stiffness, because there is a lot of similarities between endometriosis and cancer. So we thought maybe endometrial cells from endometriosis patients will have a lower stiffness compared to cancer, and similar to cancer. So we developed a microfluidic platform to test this hypothesis, coupled with machine vision. So it's a simple idea that was presented before for mechanical stiffness measurement, which is we force the cells to flow inside a narrow microchannel. If these cells are soft, they can deform easily and flow inside this microchannel at a high velocity. If they are stiff, they would get blocked at the entrance or flow inside the channel at a low velocity. Okay, so the velocity would be a measure of the stiffness. High velocity means a soft cell, low velocity means a stiff cell. So just to give an idea, so this is a video of cells. The top two videos are from cells from a healthy woman, and the bottom two videos are from an endometriosis patient. The first video is the raw video, and the second one is always the processed one. So if I just play them, so you can see once the cell goes inside the microchannel, the program can detect it and can measure the velocity as it flows inside the cell, and then it gives you the average velocity at the end. Just these videos are recorded at like about 4,000 frames per second. So what you see now is slowed down 150 times, so we can analyze hundreds of cells per second. The program also will be able to track the cell size because it has an effect on the velocity. So we use this platform to test about 9,000 cells from 6 control cases and 7 endometriosis patients. And we found indeed that there is a significant difference in the velocity of cells from patients, from healthy women. So from patients, the velocity was about 98 millimeters per second, whereas for patients, it was 98 millimeters per second. And for control cases, healthy women, it was about 50 millimeters per second. So this can be used indeed as a biomarker for diagnosis of endometriosis. And the selection of the cutoff velocity to decide whether a suspected patient indeed has endometriosis or not depends on the sensitivity and specificity you want. So if you want high sensitivity, then you need to decrease the threshold velocity at which you make your cutoff value, because this will capture any, increase the chances of capturing a suspected patient, even if it has slightly low stiffness, her cells. If you'd like to increase the specificity, only capture those that will definitely have endometriosis, then you need to increase the threshold velocity. Now, one good thing about this platform is that the biopsy we use for the analysis can be obtained using correct and an outpatient procedure. We don't have to do any laparoscopic surgery, and we have to remove all the long delay time that the patient go through before. Of course, we have to digest the tissue and culture it in the lab for a couple of days before we can do the test. But still, it's much quicker than doing a laparoscopy. And actually, it's this point that led us to, further development of this project that we would like to hopefully we can present soon. And it's we thought, okay, instead of doing the tissue digestion of device in the lab to be able to get the cells, can we do the tissue dissociation on the device itself so that we can obtain a suspension of single cells and then run it through the measurement, stiffness measurement directly or not. So this was the vision. Actually, we finished the first part. We were able to develop a microfluidic device for tissue dissociation. You can put just a chunk of tissue, 4 milligrams, flush enzymes like trypsin and collagenase, and you'll get a suspension of single cell at the end. And then we can proceed with flushing them inside the narrow microchannels to get the velocity measurements and into the diagnosis. I hope I can present this soon in µTAS, and I'll take this opportunity to encourage everyone in the audience to try to attend µTAS. It's a truly interdisciplinary conference. You see researchers from engineering, physics, chemistry, biology, and of course, medical and pharmaceutical sciences. There is a lot of translation research. Most of the research is ready to be moved from the bench to the bedside. And there is a wealth of events taking place that will make sure you leave the conference with more information, and of course, fun and excitement. Thank you very much. And I would like to conclude by thanking my collaborators and students. And thanks, Ryan, for having me.
Thank you for coming. It's always exciting, or at least for me, to see these mechanical means of cellular characterizations. And actually, coincidentally, we have Professor Dina DiCarlo during our Americas session later today at 1:30 p.m. Eastern Standard Time, who also, kind of works in this area as well. And so, basically, stay tuned for later today when we'll have sessions from the Americas, and then even later tonight, in terms of Eastern Time, we actually have sessions from Asia and Oceania. And so for now, thank you so much to our guests for coming and talking about their research. And I look forward to seeing all of you, hopefully, at µTAS 2021. Thank you again.
See you. Bye.
Thank you. Thanks, Ryan.